Hello, this is Nitin Dahad with the Times. Welcome to this latest edition of Silicon Grapevine, brought to you by the Electronic Systems Design Alliance, or ESDA, which is a community within Semini. And my guest today is Paul Cunningham, who's the Senior VP and General Manager for Cadence Design Systems. Paul, hello, how are you?
Hey, Nitin. I'm doing good and glad to be here with you on the show today.
Well, I'm glad to have you. I think it's your first time with us. So, like I start all these episodes, I think like to learn a little bit about the person I'm speaking to. So just tell us a little bit about you and how you got into what you're doing.
Sure. So I lead the kind of the verification and validation group at Cadence, and also our corporate Agentic AI initiative. So everything that we're doing, on a horizontal basis to transform our business from a company that kind of licenses you these classic EDA CAD tools to a company that's going to license you virtual engineers. I actually started out early 2000s. I'm a computer science grad out of Cambridge University in the UK. Someone
Right.
that just loved writing computer programs as a kid, was just enamored with algorithms and the wondrous things you could do with programming. And of course, I think electronic design automation CAD tools are some of the most complex algorithms in the world, right? So it's like, if you're into computer science, it's a bit of a kid in the candy store. So it was a natural
Yeah.
fit. It was great for me. I ended up doing a little startup out of university that was actually focused on doing useful skew and clock gating. So it was in a very different domain to where I am focused today. But yeah, it turned out it worked. We actually carved out a little niche, and the company sold to Cadence in 2011. And actually today, so we still, the Cadence clock tree synthesis R&D team is based out of Cambridge in the UK
Right.
primarily, and the clocking engine in Innovis, our flagship physical design tool, is it's probably been a lot's been rewritten and evolved since then. But yes, it does have its origins back in the little company that I was a part of coming into Cadence back then, and it's been a wondrous ride since. I mean, I think talk about lucking out and being in the right place at the right time, and just this whole explosion of semiconductors and custom ASICs and domain specific silicon and accelerated computing, and all of that. I mean, it's just it's wonderful. Cadence gets to be a little part of everything that the whole electronics and semiconductor ecosystem is doing.
Yeah. Just stepping back a little bit. You know, when you started, I think it was that era of like the whole computer boom and in the UK, and everybody was into computers. So it actually is not just about what we see today. There was a lot more, hands-on stuff, wasn't there, in terms of coding and playing with boards and stuff like that, wasn't it?
Yeah, absolutely. I mean, it was very, very visceral. And I think our first computer at home, my dad unveiled it once, as a Christmas thing. I think it was an Amstrad uh, with what was the operating system? CPM Plus. It had a little green
Yeah.
cathode ray display, and anyway, I found in there in the reference manuals that it had a basic programming language that was supported, and off I went. I mean, that was it. I was hooked.
I started on a Amstrad PCW8256 word processor
Oh, wow, you have better
when
memory
I
than me. I
started.
definitely can't remember the letters that came after the Amstrad.
Well, it's the 256, the 256. So, but anyway, but it's quite a, so, I mean, coming to the topic of today, and really it's about virtual engineers, the future of EDA. Why don't we go into a little bit about why agents? Why do we need agents? Why is Cadence looking at that? And why is the industry looking at it?
Sure. Yeah, I mean, actually, if you dial back, you know, further back to when I was just a kid at least middle school, maybe even elementary school. So Cadence went public. It formed as the merger of two businesses and went public, I think, in 1987.
Yep.
So you're talking like give or take 40 years ago.
Yep. I
Um,
met Joe Costello in '86. So
oh, there we go. Yeah, and if you actually
SDA.
look at the original business plan for Cadence, it was all around how it's going to uh, transform productivity for the design and verification of integrated circuits. So fundamentally, in the very beginning, right, you would literally draw transistors and lay out transistors by hand in something that wasn't actually that different to a drawing program, right? It was, really, layout in the classic sense of graphical design. And actually, interestingly, the 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 part of Cambridge University that was studying EDA actually came from the graphics side of the computer science department, because originally it was a very graphical thing. It was shapes and
Yep.
polygons on master layers. So, but of course, and I think in the early days, you used to literally measure the productivity of your organization based on how many transistors a person could draw per week. So of course, you fast today, there's no way you could do, as we have today, 100 200 billion transistor chips if they were all
Yep.
laid out by hand. So kind of the industry that we're in is all been around enabling humans to do more than they could do on their own. So, we've created abstractions, right? We created the idea of a transistor netlist, the idea of gate level, AND gates, OR
Yep.
gates, flip-flops. We raised it up. We had the innovation of what you called register transfer level,
Correct.
RTL design, so Verilog, VHDL. And at this point, actually, the source code for a digital chip has all of the look and feel of a software program. You can actually create data structures. You've got for loops, you've got while loops, you've got case statements, if statements. You're actually, coding at a pretty high level of abstraction. All of that, and I think combined with leveraging hierarchy and replication, right? Not every transistor is unique, right? So memories have, of course, a lot of structure and replication, but even, multi-core CPUs, right? It's the same core replicated. So hierarchy, replication, abstraction, probably I'd say are the three, really biggest things that have enabled us to go from drawing transistors by hand to doing hundreds of billions of transistors in a modern integrated SoC. So the big question is, okay, where to next? So now I think we if you look at the last sort of 5 years or so, there are real concerns over how to push productivity to the next level. And I see that, when we talk to, pretty much all our customers around the world, they're just staring down, they're looking at their product roadmaps and saying, there is no way that we can hire enough people fast enough to execute on our roadmaps. So there really is this like literally productivity crisis. I think it's been well published and covered.
Yes.
Yeah. So kind of where to next? And I think what we've got now, with the onset of AI, in particular agentic AI, large language models, is this transformational moment in computer science history where we can actually humanize software. Until recently, if you wanted to interact with computer software, it was very precise. You had a precise language, you had a precise user interface, buttons you had to click, dialog boxes, whatever you did. If you weren't absolutely perfect, wasn't gonna work. It would error out. One typo in your source code, it's gonna error out, and you have to, fix it before it will compile. Whereas, agentic AI is not like that. It's actually pretty human. You can talk to an agent, and it can talk back at you. And if I, just as you and I are talking now, if I make a grammatic error, or we're talking over email, if I have a spelling mistake, it doesn't matter that much. You're still going to get the point across. So the ability to interact in natural language, in pictures, in diagrams, in text, it is transformative. It means now we can start to automate things that previously we never could. And if you look at the types of things we're automating, they're human-like. And now we look to really the moment, literally right now, January, February, March 2026, and it's all about agentic teams, system of agents. We're actually starting to find that these software programs can actually perform tasks that start to look pretty sophisticated. They can really create entire software programs. They can generate entire verification environments. They can plan verification. They can validate things. They can iterate. So I think we are on this journey where, ultimately the next level is that at some point, what you'll be able to license in every sense of the word is like a virtual human being. You really couldn't, you can interact with it. You can give it the touch, just like if I'm, making a Zoom call now, I'm sending an email to a real engineer on my team. You could give it the same level of abstraction, the same kind of instructions to a software program using exactly the same forms of communication, languages, diagram, whatever, and it will go off and do the work for you. So I think, when we get to that point, it will really be the case where productivity is limited only by compute. The only thing that's stopping you having more virtual humans is how much compute you've got available to actually run those virtual humans. And yeah, I think it's just such an amazing time. I will caveat, we are absolutely not there yet,
Okay.
and it's moving, but it's moving very, very fast. And at least for the last year or so, every time I think something's going to take X months to happen, it happens in like X over 10 months. It's happening 10 times faster. So the gradient is just unbelievable right now. And certainly by the end of the decade, you're going to, the perception of Cadence as a business is going to be totally different than it is today.
Well, I mean, you've sort of described a real utopia, and for a lot of people, I mean, you at Cadence talk to a lot of engineers. Do they actually can they visualize what a virtual agent looks like, or what will it mean on their desktop, or how does it work? Is it just like uh, you just put a command and something's running in the background as an agent? How does that work?
Without kind of getting it into the weeds too much,
Yeah.
if you look, the kind of way we got is the basic foundation model, what you originally called one shot or zero shot, right? You'll put in a prompt and it will give you a response,
Okay.
and that's your kind of your unit level horsepower, if you like, or raw intelligence of that foundational model. And then there's a number of different providers. There's commercial models, there's open weight, open source models. What you can then do, though, of course, is you can start to build expert systems around them. So you can, if I provide a prompt, a question to an LLM, under the hood, the software wrapper around it may augment that prompt with additional instructions, additional tips. It will say, okay, here is your question, but here is a whole bunch of additional information or additional suggestions about how you might answer that. So that's what's kind of broadly referred to as prompt engineering. And you can
Okay.
actually, you can think of prompt engineering as really computer programming, but for an LLM. So,
Right.
instead of writing C or C++, you write a prompt to what's now been increasingly called a skill. And actually,
Right.
the language you write that skill in is natural language, right? It's just in English, for example, or Mandarin or French or any other language. And then you can also build systems that say, well, once I get the response, I might then feed it back, right? I might modify, I might go take that response and run a classic other product, a classic EDA tool from Cadence, a simulator, a formal tool, a place and route tool, and use that to get additional information and then circle back. So you're going to do multiple prompts together in some kind of sequence or graph, and that's generally called reasoning or multi-shot. And but I think in classic computer science, it's essentially an expert system that is built around large language models, and so we're constructing these now, and they have, within certain guardrails, they kind of get there, but they quite often will need to come back to the real human for a check-in or for help, or they'll start to go off the rails and you'll have to kind of shut them down and bring them back. So they need a lot of hand holding, and it's the kind of gradual progression of less and less hand holding and more sophistication. And I think it won't be black and white. There'll just be a moment where we'll call it and say, this is really a virtual engineer, not a assistant or whatever, or an agentic helper or something else that you don't really
Yeah.
use a human term to describe.
And I think that's my point. I don't think people will see it as a like something physical or whatever. It's just part of that whole environment.
Yeah, it's a progression, it's a journey and evolution, and it really, it's like a three-legged stool, because one part of that is the classic EDA tools, the core capabilities, the core engines that we have, which of course need to be, they're going to be run increasingly by the agents rather than real humans, but they're absolutely there. They're not going anywhere. And then you've got the actual LLMs themselves, the foundation models, the fine tuning, the additional skills and capabilities that they're putting in natively into these LLMs. And then you've got the actual customers, and they've got all the data, all their chip design history, all their knowledge, their specifications, their repository. So between the knowledge and the data of our customers, the foundation model providers, and the Cadence, computational software, classic science, physics-based tooling, the three together, how do we create this kind of virtuous cycle, this virtuous ecosystem where we
Yep.
really, deliver essentially this next generation of productivity.
Let's move to the practical use of virtual agents. I'd like to get some understanding of where you've seen it used and maybe some typical customer examples. You've announced some, so maybe just give us some ideas so the audience can understand that.
Sure, sure, absolutely. So maybe I'll answer it in two parts. So I think one thing to point out here that's quite important is, a large language model, essentially, kind of token processor, a natural language processing technology isn't the only form of AI. So actually AI as an actual concept is 40, 50 years old. But I think in terms of more recent history, really for us at Cadence, 2016 was a pivotal moment when DeepMind, Demis Hassabis came up with AlphaGo and really showed that you could use neural networks, convolutional neural networks to do deductive reasoning and actually play, the game Go, right? Where previously everyone was doing kind of search-based techniques, a tree of possible moves and trying to prune it with heuristics and other things that showed actually this kind of intuitive predictive technology could be very, very effective. You could train it. And so these more traditional reinforcement learning, classic machine learning techniques since 2016, they're very effective too. You can put them inside tools. You could use them to make a place and route tool get you better power, performance, and area. You can use it in logic simulation to, hit coverage faster. So actually that's really been, so they are really there. And we have in our tools already for 5 or 6 years, and this is mass deployed, thousands of users, thousands of tape outs, whether it's
Okay.
to get better formal proof, to get better logic simulation, better PPA and physical design. So that's actually already done and is very, very proven and mainstream. And a lot of the time, our customers don't even necessarily realize that a result they got was actually empowered by AI under the hood. Now, to the current chapter, to agentic AI, large language models humanizing our software, I'd say the tip of the spear and something, we had a big launch, a couple of weeks ago, is to really look at the closest analogy to a coding assistant. If you think 2025 was a transformative year for the software engineering community, where agentic AI really showed that it could make computer programming, classic software programming, orders of magnitude more efficient. So the closest analogy to that in the chip world is this big digital design. So I remember I mentioned coding in languages like Verilog and
Yep.
VHDL. So the source code for a big digital chip is quite similar to a software program, although it's also different in other ways. And so we feel that the agentic digital chip design and verification is really going to have a breakthrough right now. And so we've launched what we call our first super agent, the chip stack super agent, for doing exactly that. We had endorsements from Qualcomm, from Altera, from NVIDIA, from Tenstorrent, and really quoting, measurable, quantified benefits, but relatively narrow. So a specific task around generating a test plan or around generating a formal verification bench. But in each case, showing, very, very significant improvements. And so the overall system has the look and feel of a full kind of verification engineer, but it's definitely a strong human in the loop. There's a lot of checking back in with you, a lot of steps, but we absolutely see that, over the next 6 to 12 months, we think it's going to be really starting to proliferate at scale and having a big impact on our customers' productivity.
That is interesting. What about well, where's this all going? I mean, what do you see in the? I think you said by 2030, by the end of the decade, we'll pretty much see all of this. But fast forward 10 years, what does the industry look like? Or can we even imagine it?
That's a great question, Nitin, and I won't for a second pretend to be able to truly know.
I don't think anybody can today.
No, but I love to dream, and
Yeah.
it's a wonderful thing to think about. I mean,
You could be
I
termed the
don't
Asimov of
believe.
our era.
Yeah, no. Well, I think one thing I would say, I do not think that the large language model, as we know it today, is the end state. So this, big sequence of multi-layer perceptrons, um, structure with attention mechanisms. This is a structure which is inherently asynchronous. Acyclic, right? There's no loops, there's no recurrence actually in
Mm.
LLMs today, and it's something where training and inference are very, very separate. So when you're using an LLM, the weights are not changing. And then when you're training it, you're figuring out the weight. And a human brain is nothing like that. The human brain is densely recurrent, all the neurons, it's all bidirectional. I am both having a wonderful chat with you now, but I'm also learning and remembering from it. And so, the weights in my brain are being continuously updated. So
Yeah.
the whole way that you kind of think and reason, which is very closely coupled to loops and feedback, right? And the way you learn. So I think there are huge breakthroughs still to come at the fundamental, research lab level of AI. And so to me, if you take a 10-year view, that's the big question. It will not be LLMs and it will not be agentic systems as we know them today. They will be very
Mm.
different because there'll be new fundamental innovations right at the bottom of the stack in terms of how an LLM is actually structured and how it is trained and how it is used. And I'm certainly not,
Yeah.
I have no idea what that will be, but it will be different, I believe, for sure. And that difference will give another leap in intelligence, right? And another leap in
Mm.
productivity and application. Probably say the other thing, of course, to call it is, AI is absolutely now moving to the physical world, right? So,
Yes.
autonomous vehicles, robots, drones, factory automation. So physical AI, that's very, very, and I think the next 5 years are going to be just phenomenal there. And I mean, I know we see just this amazing investment and amazing growth in AI infrastructure, but I think physical AI and AI into the physical world could be even bigger still. I mean, it's unbelievably exciting.
Well, I mean, I've seen it this year at Embedded World in Nuremberg. You could see some of the implementation of that physical AI through the whole tool chain, through the whole value chain. Sorry,
Yes.
and yeah, it is quite impressive how much engineering has sorry, how much of the concept has been delivered in that engineering that we're seeing, with companies you work with, and where we're going. But yeah, funny what you said earlier about humanoid robots, and you sort of said something about how your brain works and how we're having this conversation, and I thought to myself, all we need to do is model that, and then that creates that humanoid robot. But that's the way you just described it. It's that's kind of what we're trying to do anyway.
Yeah, maybe. I mean, in the wonders of, biology, some of the most exciting things I read about and learn. And I think we're just scratching the surface of our knowledge of what how we're built and how we happen. But yeah, I don't. It doesn't necessarily actually. In fairness, the way we create artificial intelligence doesn't have to literally model human intelligence, right? I think we don't want to also constrain ourselves there. So
Right.
it's a different underlying compute framework.
Okay.
So yeah, it may be like that. It may be honestly, it may be different, Nitin. I just don't know.
Well, I think AI will definitely change how we engineer those humanoid robots, physical AI, and everything else. But let's we've talked for a while. I just want to maybe close it off a little. Just One of the things I always ask on this Silicon Grapevine is series is, what have you learned from what you've seen through what we're doing? And I think, relevant to this conversation is, where do you see, what's the thing that you've seen from what you've seen with AI over your career, how it's evolved? And it's not a new thing, but it's just how it's all evolved. What have you learned, and what would you tell yourself today, if you know what you know now, to young Paul?
Well, apart from things like buy Nvidia stock,
Yes.
uh, yeah, no, I mean,
Yeah.
I sometimes do, I have the privilege, I visit our sites around the world, and sometimes they set up, roundtables and meetings with people, early in their career. And there's often, this kind of like, what advice would you have for me early in my career? And I mean, in many ways, it's actually the first things that come to my mind always are not technical. Um, it's about things like, this paradox that usually when you're earlier in life, you're really, trying to, both create your career, but you're also trying to, grow in the personal world, right? And possibly, have a family and other things. And so kind of trying to get the right balance between those 2 points. And I think one of the things
Mm.
that I would definitely tell a younger version of myself is this fact that, you can always take time out for the little things that are not related to work. If you have a little kid that's just doing something and a little play at lunchtime, or there's a little game after school or something, you can always take an hour out here, a couple hours out there. You can always make it up for it. You know, if of course, disappearing for a month, taking 2 months off, that's going to be really career limiting. But little things, the days are lasting. And I think with modern technology now, with like we have here, communicating over Zoom or Teams and continuously being connected, it's no problem. You can always make up for it. So yeah, don't disconnect yourself completely, right? Stay in touch, and because those little moments, they're gone, right? They're lost in time. So that's something I do feel. And then probably that other thing is, that distinction between being taught and learning. When you're at school and you're younger, everything's laid out for you, right? There's a syllabus, there's a thing, you have this expectation that you will be taught, but the real world is not like that. No one's going to teach you. So you're always
Yeah.
learning, you're always sponging up. So you need to stay curious and watch people that you feel are, more successful than you, or that you aspire to. And you have to, watch what they do, how they behave, how they interact. So you always need to sponge it up for yourself, right? And
Right.
and carve your own path, right? Take multiple inspirations, multiple sources of learning, and then make it your own way, right? Everyone's going to have their own journey in life. So there's probably, those are the two things that I talk about a lot.
Yeah.
I probably wouldn't say, unless you're making this kind of like Back to the Future type stuff. If you really know what's going to happen, then you'll buy certain stocks or invest in certain things. But I don't think
Yeah.
that's the kind of
Yeah.
useful feedback to give anyone, of course.
No. So I think the key point that I love that is carve your own path and balance. I think
Yeah,
that is actually quite good. Well,
absolutely. Yeah.
Paul Cunningham, thank you very much for being a guest today on Silicon Grapevine, which is brought to you. This episode is brought to you by the Electronic Systems Design Alliance, which is a community within SEMI. Thanks once again, and see you on the next episode. Bye.
Bye-bye. Thank you so much, everyone.